An ideal gas is a gas that behaves in a hypothetical way, making any calculations or computations somewhat easier because the constituents of an ideal gas do not interact or react with each other. The ideal gas law assumes that individual molecules are just point masses that do not react with other point masses. Ideal gases use the ideal gas law, PV equals nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of gas present, R is the ideal gas constant, and T is the temperature of the gas. The ideal gas law can also be written in terms of molar volume, V bar. V bar represents the volume divided by the number of moles. The ideal gas law becomes P multiplied by V bar equals R multiplied by T. The ideal gas law is the combination of four different laws: Boyle's law, Charles's law, Gay-Lussac's law, and Avogadro's principle. Boyle's law explains the relationship between pressure P and volume V through the equation P times V equals some constant K1. Here, temperature and the number of moles are assumed to be constant. Because pressure and volume multiply together to give some value to K1, and K1 is a constant, if the value of one variable changes, so must the other. In this case, if pressure increases, the volume must decrease to keep the value of K1 constant. We say that pressure and volume are inversely proportional. Boyle's law can be extrapolated further to describe isotherms. Isotherms are cases where the temperature is constant, as well as the number of moles of the gas. At constant temperature and with a constant number of moles, P1V1 equals P2V2 for gases 1 and 2. Charles's law explains the relationship between volume V and temperature T through the equation V divided by T equals some constant K2. This relationship assumes constant pressure and a constant number of moles, and shows how, if one variable increases or decreases, so must the other, in order to keep the value of K2 constant. Therefore, volume and temperature are proportional. At constant pressure and with a constant number of moles, V1 divided by T1 is equal to V2 divided by T2 for gases 1 and 2. Gay-Lussac's law relates temperature T and pressure P through the equation P divided by T equals some constant K3. In this law, volume and the number of moles are assumed to be constant. Then, if the pressure increases or decreases, so must the temperature, in order to keep the value of K3 constant. Pressure and temperature are said to be proportional. At constant volume and with a constant number of moles, P1 divided by T1 is equal to P2 divided by T2 for gases 1 and 2. Finally, Avogadro's principle relates the number of moles N to the volume V. In Avogadro's principle, both pressure and temperature are assumed to be constant, so the relationship is V divided by N equals some constant K4. If the number of moles increases or decreases, so must the volume. Therefore, the number of moles and volume are directly proportional. However, it should be noted that more volume of a gas is not characteristic of the gas itself. At constant pressure and temperatures, V1 divided by N1 is equal to V2 divided by N2 for gases 1 and 2. Combining Boyle's law, Charles's law, Gay-Lussac's law, and Avogadro's principle is how the ideal gas law was developed. It combines the relationship between pressure, temperature, volume, and the number of moles for ideal gases in one equation. Another valuable equation for ideal gases is Dalton's law, which explains the commutative effect of pressure. If one wants to understand the total pressure of multiple gases with different pressures, Dalton's law explains that the total pressure is equal to the sum of all the pressures for the individual gases. This relationship can also be rewritten to determine the pressure of one gas if the pressure of the total system is known. For this, the value of chi sub I must be calculated by dividing the number of moles for one gas species by the total number of moles for the system. Then, x sub I can be multiplied by the total pressure of the system to find the pressure of a particular gas I. Dealing with ideal gases is wonderful, but in the real world, most gases do not behave ideally. In real gases, the particles may interact. Thus, the ideal gas law is too simple to handle real gases. This is where the van der Waals equation comes in. In addition to the familiar variables of the ideal gas law, the van der Waals equation adds the terms A and B. A represents the volume of the particles and is known as the repulsive term. B represents the particle interactions and is the attractive term. The closer the values of A and B are, the more ideal the gas becomes, and the more closely the van der Waals equation represents the ideal gas equation. It should be noted, though, that the van der Waals equation is still an approximation and does not apply to every gas. The van der Waals equation is written as P equals RT divided by the difference between molar volume and the value B, then subtract the quotient of A divided by the square of molar volume. Forces of concern that further affect the behavior of gases are gravity and electromagnetism. Gravity is a factor because everything that has mass has gravity, so gases, although they have minuscule amounts of mass, also have super small gravity. Electromagnetism is important because it affects the compressibility of a gas. Imagine trying to compress a gas. At some point, the particles will get so close together that they will start to repel each other. This is the repulsive force given by the variable A in the van der Waals equation. Gases cannot compress further because of these Coulomb interactions. If the van der Waals equation does not work for a particular gas, the Varial equation should be tried next. The Varial equation accounts for increasingly more interactions between molecules in a gas and is written as follows. P equals RT divided by the product of molar volume and a series of summations of 1 plus B divided by molar volume plus C, divided by the square molar volume, and so on, increasing the terms and the degree to which the molar volume is raised. This is a series that can go to infinity. The value of B represents the interaction between pairs of molecules, i.e. 2 molecules. C represents the interaction between triplets, or 3 molecules. If more than 3 molecules are present, more terms are required. Let's move now into classical thermodynamics. As applied to chemistry, classical thermodynamics is only concerned with 3 things: energy, heat, and work. In chemistry, energy is denoted by a capital U, heat is written as a capital Q, and work is denoted by capital W. Heat and work are distinguishing of thermodynamics and differ from energy. Variables in classical thermodynamics can be either extensive, meaning size-dependent, or intensive, meaning independent of size. They can also be either state or path variables. A state variable describes the state of the system, i.e. the system has a certain temperature, not heat. State variables are independent of the path between initial and final states. For example, if you were traveling from Los Angeles to New York, you would likely fly and not care about the route the plane takes, only the distance between the 2 cities. In that case, distance would be a state variable, with the distance you traveled being the difference between New York and Los Angeles. Energy is a state variable. The change in energy can be written as the final energy minus the initial energy, or expressed as an integral from the initial to final state. Never use any state variable without the delta denoting change in front of it. Heat is not a state variable, so it cannot be expressed as an integral, nor can the change in heat be explained as the simple difference between final and initial states. Heat, as well as work, are both path-dependent, meaning they describe the path. Path is a curve in the space defined by the changing variable that represents a process. As an example, this would be the route taken to drive from Los Angeles to New York. The definition of path variables requires integration, but it uses inexact differentials, denoted by the differentiated variable with a line striking through the top of the D. Inexact differentials are not equal to the final state minus the initial state. The first law of thermodynamics says that the energy of the universe is conserved. One could say the change in energy is equal to the sum of heat and work, but this would not be well defined. In actuality, it is the total energy that is the sum of heat and work. This relationship is written as the differential equation du equals the inexact differential of Q plus the inexact differential of W. The energy of the universe was set at the Big Bang and has never changed. Unfortunately, we are unable to determine that value, but we can calculate the change in energy. This concept can be understood by comprehending the history of temperature scales. Both the Celsius and Fahrenheit scales were developed before anyone knew there was an absolute zero temperature. The scales were quantified based on what could be measured. Only much later was absolute zero temperature able to be defined by the Kelvin scale. Physical chemistry uses a sign convention to understand the flow of properties into and out of a system. Chemistry is focused on the system, therefore the sign convention is based on the flow with respect to the system. When energy or work flow into or are put into the system, the convention is to use a positive sign. When the energy or work flow out of or are taken out of the system, the convention is to use a negative sign. The same can be said for energy. Energy into the system increases the energy, positive U, while energy removed from the system decreases the energy, negative U. The change in energy of the universe is the change in energy of the system plus the change in energy of the surroundings. Using the first law of thermodynamics, which says the energy of the universe is conserved, we can set the change in energy of the universe equal to zero. Then, rearranging the equation, we find that the change in energy of the system is equal to the negative change in energy of the surroundings. In other words, if energy is added to a system, it must be taken from the surroundings, depleting the amount of energy of the surroundings. Returning to the earlier equation of du equals the inexact differential of Q plus the inexact differential of W, we can replace du with the value of 0 to represent no change in the energy of the universe. Then we see the relationship the inexact differential of Q is equal to the negative inexact differential of W. There exist both open and closed systems, which differ in their ability to exchange matter. Open systems exchange matter with their surroundings, while closed systems cannot. However, both systems can exchange energy with their surroundings. A third type of system, an isolated system, cannot exchange energy nor matter with its surroundings. The walls enclosing systems are also important to think of in this regard. Some walls do not allow the transfer of energy. They are called adiabatic walls, and they insulate against the transfer of heat. Some walls do allow the conduction of heat. These are called diathermal walls. Thermodynamic equilibrium refers to a condition in which equilibrium exists with respect to pressure, temperature, and concentration. Equilibrium may be established with respect to a given variable only if that variable does not change with time and if it has the same value in all parts of the system and surroundings. If two systems enclosed by adiabatic walls are brought into contact with each other, it is not possible for them to reach thermodynamic equilibrium with each other because the adiabatic walls insulate against any heat transfer that might occur. Diathermal walls, by contrast, can allow systems to reach thermal equilibrium because they conduct heat. The zeroth law of thermodynamics deals with this concept of thermal equilibrium. It states that if two systems are separately in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other. Using this law, we can determine if two systems are in thermal equilibrium without ever bringing them into contact with each other. Now, to reiterate a few details about the variables in these laws. Pressure in a gas is the random, thermally induced motion of individual molecules. The pressure exerted by a real gas can be either larger or smaller than the pressure of an ideal gas under the same conditions. In an ideal gas mixture, the total pressure is the sum of the partial pressures. Temperature can only be measured indirectly through a physical property such as the volume of a gas or the voltage across a thermocouple. Equations of state relate to state variables. The reliance on the size of the system determines whether a variable is intensive or extensive. An intensive variable is independent of the size of the system, and an extensive variable is proportional to the size of the system. The van der Waals equation of state takes both the finite size of molecules and the attractive potential into account. Changes in the internal energy and enthalpy of a system depend only on the initial and final states of the system. Work and heat flow are responsible for changing the energy of a system and depend on the path between the initial and final states. Energy can be neither created nor destroyed. As the first law of thermodynamics says, the internal energy U of an isolated system is constant. The energy of a system can only be changed by the transfer of heat or work between the system and surroundings. Heat is the quantity of energy that flows across the boundary between the system and surroundings, because there exists a temperature difference between the system and the surroundings. Heat will always flow spontaneously from high temperature regions to regions with a lower temperature. Heat is transitory and only appears during a change in state of the system and surroundings. If Q is positive, the heat is deposited in the system. If Q is negative, then heat is withdrawn from the system. Work is any action that transfers energy across the boundary between the system and the surroundings. It is associated with a coordinated motion. Work results when a force in the surroundings causes a displacement in the system along the direction of the force. Work is transitory and only appears during a change in state of the system and surroundings. The net effect of work is to change the energy of the system and surroundings. If, in doing work, a mass in the surroundings is lowered, then the work is also lowered. By convention, work is positive when the work is done by the surroundings, and work is negative when it is done by the system. Important to note is that thermodynamics can only be applied to systems in internal equilibrium. In quasi-static processes, the system passes through a continuous succession of equilibrium states. A process is reversible when an infinitesimal change in the direction of the variable that drives the process causes a reversal in the direction of the process. A process is irreversible when an infinitesimal change in the direction of the driving variable does not change the direction of the process. Work for both reversible and irreversible processes can always be calculated with the equation work equals the negative integral from the initial to final volume of the external pressure multiplied by the differential volume. Evaluation of this integral requires that the functional dependence of the external pressure on the volume be known. Unlike the case for reversible expansion, only the surroundings-based calculation can be carried out for an irreversible expansion or compression. The change in value of a state function depends only on the initial and final states, and not on the path between them. The state function depends only on the state of the system, and not on the path taken to reach the state. Work and heat are both path functions, so there are no exact differentials for work and heat. Incremental amounts of these quantities are denoted instead by dW bar and dQ bar. Note that the line, the bar, goes through the top of the D. The amount of work that can be extracted by a process is maximized if the process is reversible. At the molecular level, work is associated with changes in the allowed energy levels, whereas heat is associated with changes in the population of the energy levels. The thermal response of a system to heat flow is called heat capacity. Heat capacity is a measure of the energy needed to change the temperature of a substance by a given amount. It is represented by the capital letter C and is given in terms of the SI units joules per Kelvin. Heat capacity is an extensive quantity in which the molar heat capacity, given in units of joules per Kelvin per mole, is an intensive property. The heat capacity of a substance depends on the values of its rotational and vibrational energy levels, the temperature, and whether it is a gas, liquid, or solid. For a given substance in the gas phase, the heat capacity at constant pressure is greater than the heat capacity at constant volume. For either the liquid or solid state, the heat capacity at constant pressure and the heat capacity at constant volume are approximately equal. Energetic degrees of freedom are referred to as translation, rotation, vibration, and electronic excitation, each with its own set of energy levels. The change in energy can be measured by carrying out a process at constant volume and determining the heat Q. In mathematical terms, delta U equals Q sub V. Delta U can be experimentally determined by measuring the heat flow between the system and surroundings in a constant volume process. Enthalpy is a state function given by the symbol H. H equals U plus P times V. Delta H can be measured by carrying out a process at constant pressure and determining Q. In mathematical terms, delta H equals Q sub P. The adiabatic expansion and compression of gases is an important meteorological process. Reversible adiabatic compression of a gas leads to heating, while reversible adiabatic expansion leads to cooling. There exist easily measured thermal expansion and compressibility coefficients that are directly related to partial derivatives. The isobaric thermal expansion coefficient is represented by alpha and is equal to 1 over V multiplied by the partial volume divided by partial temperature at constant pressure. The isothermal compressibility coefficient is represented by kappa with the subscript capital T. This coefficient is equal to -1 over volume multiplied by the partial derivative of volume over the partial derivative of pressure at constant temperature. The heat capacity at constant volume is a direct measure of the partial derivative of energy with respect to temperature at constant volume. Energy is only a function of temperature for an ideal gas, and the energy for an ideal gas does not depend on volume. Energy is only a function of temperature for real gases and processes that do not involve unusually high gas densities. For real gases, liquids, and solids, the dependence of energy on temperature is much stronger than its dependence on volume. Under most conditions encountered by chemists in the laboratory, energy can be regarded as a function of temperature alone for all substances. The heat capacity at constant pressure is a direct measure of the partial derivative of enthalpy with respect to temperature at constant pressure. Enthalpy does not depend on pressure for an ideal gas, and, with the exception of large pressure changes, enthalpy does not depend on pressure for liquids and solids either. Thus, except for large pressure changes, enthalpy can be assumed to be a function of temperature only for solids and liquids. The Joule-Thompson experiment is an experiment where gas is forced through a porous plug using a piston and cylinder mechanism. The pistons move so as to maintain constant pressure in each region. There will be an appreciable drop in pressure across the plug. Then the temperature change of the gas can be measured. This experiment improved upon the Joule experiment because it allows the partial energy to partial volume ratio at constant temperature to be measured with a much higher sensitivity. It also allows for the measurement of the partial derivative of enthalpy with respect to pressure at a constant temperature for real gases. In the Joule-Thompson experiment, the pipe is insulated so the heat is equal to 0. Enthalpy is constant in the gas expansion, so the expansion is deemed isenthalpic. There also exists a Joule-Thompson coefficient μ that is described mathematically as the limit as the change in pressure approaches 0 of delta T over delta P with respect to enthalpy, or more succinctly, the Joule-Thompson coefficient is the partial derivative of temperature over the partial derivative of pressure with respect to enthalpy. If this coefficient, the value of μ, is positive, then the attraction part of the potential is dominant. In other words, a decrease in pressure leads to a cooling of the gas. If μ is negative, then the repulsive part of the potential dominates. More simply, expansion of the gas leads to heating. μ will be equal to 0 for ideal gases since the particles in ideal gases never interact and therefore will not experience any attraction or repulsion. It is the dependence of enthalpy on pressure at a constant temperature that allows real gases to be liquefied. Thermochemistry investigates the heat flow into or out of a reaction system. For a reaction that occurs at constant volume, the heat that flows into or out of the system is equal to the change in energy for the reaction. Conversely, for a reaction that takes place at constant pressure, The heat that flows into or out of the system is equal to the change in enthalpy for the reaction. In an exothermic process, heat is transferred from the system to the surroundings, while in an endothermic process, heat is transferred from the surroundings to the system. Most of the internal energy or enthalpy of a molecule is stored in the form of potential energy in chemical bonds. Therefore, energy can be released or taken up as bonds are made or broken. This has been an episode about physical chemistry. Thanks for listening to Fall Asleep to Science.